I would like to invite our associate professor Meelis Kull to introduce our first main speaker.
Welcome from me as well. I'm very honored to introduce to you our distinguished guest and speaker, Eyke Hüllermeier, who's a professor at LMU Munich and has been a professor at several other universities in Germany, in particular in University of Paderborn, where he had done his PhD. He's really well known in the field of machine learning and artificial intelligence. He's leading a big group in this field. He has contributed in many topics that are fundamental in machine learning. For example, preference learning, also active learning, also bandits, many other topics. But particularly today, he's presenting a topic in which maybe he's even the best known is uncertainty quantification. And he's given several tutorials on this topic, but now we have the chance to see him live here at ESCAS. So welcome, Eyke, please.
No.
Now you're okay.
Now I'm muted? No, I'm unmuted, okay. I had to do this blindly behind my neck. Yeah, so thank you very much, Meelis, for the welcome and the kind introduction. It's a pleasure for me to be here. It's my very first time in Estonia. My first impression is very positive. Everything is very nice. The people are kind. The weather is good. The hotel is great, so everything is fine. So Meelis already said what I'm going to talk about today, uncertainty quantification in machine learning. And yeah, before starting, let me say that I would prefer to have this tutorial as interactive as possible. So first of all, whenever you have a question, please feel free to raise your hand, yeah, and ask a question. It's important that you all understand well what I'm talking about. I don't want to be too slow. I don't want to be too fast. It wasn't so easy to prepare this tutorial because I didn't really know exactly whom I'm going to speak to. What is the background of the people? How familiar you are already with machine learning, uncertainty, and these things. I hope I did it well, but please let me know if it's too boring, if you already know everything, or if it's too fast, and so on. Yeah. So let's have it interactive. Also because the tutorial, after all, it's quite long. So it's 3 slots of 90 minutes, 4.5 hours. I'm also not exactly sure that I prepared the right number of slides. So from time to time, perhaps I will skip some because preparing 4.5 hours in advance is quite a challenge. All right. So let's go into the topic, uncertainty machine learning, but let me start a little bit maybe earlier and tell you that uncertainty has always been a very important topic in AI in general, not only in machine learning, but in AI in general. And that started already in the very first days, in the very early days of AI, in the era, let's say, of expert systems, knowledge-based systems. Many of you are very young, I see, so you probably don't even remember, or perhaps you haven't even been born at that time. That was in the 80s, 90s of the last century, when knowledge-based systems, expert systems became very popular, and maybe some of you heard about expert systems such as MySyn, which have been applied in medicine and have mostly been rule-based. So the idea was that you have human experts like medical doctors, for example, who formalize their knowledge in terms of suitable formalism like rules, and then the expert system is processing this knowledge to come up with conclusions, recommendations, prescriptions, for example, of a medical treatment. And already then, people noticed, of course, that it's completely impossible to formalize such background knowledge, like medical knowledge, in a coherent way so that everything is deterministic, there is no uncertainty involved, and so on. And the first version, for example, of this Mycin system was then quite quickly extended by so-called certainty factors, where the medical doctors could provide some degree, numerical degree, of evidence in favor or against a certain conclusion. And these certainty factors have then been used in the processing of such rules to come up with not only with a conclusion, but also with a quantification of how certain or uncertain that conclusion is. Mathematically, that was all not very sound at that time. So these certainty factors have been a little bit ad hoc. Only later, quite a couple of years later, a more sound mathematical basis was provided, also with the help of generalized uncertainty calculi such as belief functions. So a little bit later, then things became a little bit, let's say, more mathematically sound. That was the big era of graphical models, Bayesian networks, for example, that some of you certainly know, where knowledge was formalized in terms of probability distributions, formalized and processed in terms of probability distributions. There is, by the way, I just remember, because these graphical models really have been very popular for quite a while in the beginning of 2000s, and so there is a specific conference dedicated to this topic of uncertainty in AI, which is called Conference of Uncertainty in AI, UAI. I have been there last week, and that has been already the 38th edition of that conference. So you see, it's almost 40 years, yeah, that this topic has a known conference, even in machine learning, in AI. Yeah, and now we are, of course, in the era of machine learning. Machine learning is dominating AI these days very much. And here you see a standard scenario, I would say, of machine learning. Basically, what is shown here is the typical setting of what we call supervised learning. So there is some training data. Oops. There is some there is some training data here. Could be, for example, X-ray images, which are labeled positive and negative, depending, for instance, on whether a certain disease is present or not. And from these data, you learn a model, which could be a neural network, for example, via a process of model induction. And this model is then used to make predictions for new instances, new patients, for example, new X-ray images that the learner hasn't seen before, then hoping that the prediction will be right. So, for example, when the system says positive, that the disease is really present, and the same for negative. And it's very obvious that uncertainty is also playing a role here, perhaps even more than in the case of knowledge-based systems. This is a completely data-driven approach, and it's clear that these models that are learned from data via this process of model induction will always be hypothetical in nature. So they are best guesses. Yeah? They are fit to the data as good as you can, but of course you can never be sure that these models are right in a sense. So this is, yes, why machine learning is inseparably connected with uncertainty. And this is mainly due to the fact that machine learning is really a process of induction. It's a kind of inductive reasoning, opposed to what has been done mostly in knowledge-based systems, namely deductive inference. And since the models that are learned from data are hypothetical in nature, so are the predictions that are made using these models. And these predictions are, of course, mostly what we are interested in practical applications. When a machine learning system makes a prediction, what we would like to know is how sure can we be that this prediction is right or wrong. So what we are essentially interested in is to quantify this, what we call predictive uncertainty, to represent our answer or the learner's uncertainty about its predictions and maybe quantify this uncertainty. So there are various other sources of uncertainty that come into play, which includes, for example, model assumptions. Yeah, you may start from wrong assumptions. You may, for example, assume some linearity where it's actually not present, where the dependency is nonlinear. You may assume that a certain input variable is irrelevant, although it's relevant, and so on. I will come to this a little bit later. Of course, also the quality of the data has a strong influence on how good your models eventually will be and how certain their predictions are. So typically you have noise in data, but when the level of noise exceeds a certain threshold, then learning may become even impossible. And this you will also see from the certainty or uncertainty in the predictions. On the other side, if you look at applications of machine learning these days, it's very clear that we would like to have some trust in these systems. So a trustworthy representation, therefore, of uncertainty is really very desirable and a key feature, should be a key feature of modern machine learning methods, especially in safety-critical domains, like, for example, autonomous driving, just to pick one example, or medical diagnosis, the example we had seen before. In applications of this kind, we would not only just our machine learning system to make a prediction, this is positive, this is negative, or I don't know, the driver is looking to the left or to the right or straight ahead. Instead, what we would like to have is a representation of how certain or uncertain the learner is about this prediction. We would perhaps also like the system to abstain from making a prediction or a decision in cases where it is too uncertain, and then in the case of autonomous driving, for example, hand over to the human driver, or in the case of medical diagnosis, to let the human expert, the medical doctor, take the decision and so on. Or perhaps to produce a prediction in the form of a set of possible predictions, of possible outcomes, like, for example, a confidence set in statistics or confidence interval in statistics, instead of just letting the system make a point prediction. Also connected to uncertainty is, of course, trust, I said already, and robustness. You probably all heard about these problems with adversarial examples, which are well known for images, but you can also have them in text. So here, for example, I took this from the literature. You have a piece of text, and to this was applied a machine learning system to decide about the sentiments, so whether the text is mostly positive or negative, expressing a positive opinion or a negative opinion. And you see that the system is making the right prediction here. And then you change only one single word. You replace the this by a that, and this is even a very unimportant word, actually, and suddenly the prediction turns to positive, No clue exactly why, but this happens, and this is certainly something that shouldn't happen, If a system is behaving in this way, that certainly doesn't help to have trust in the system and the predictions it makes. It doesn't work anymore. I can stop here. The pointer still works, but forth and back doesn't work anymore.
Was this a real example or
yeah.
Made up?
No, no, no.
It was a real example.
It's a real example, yeah. I took from the literature. Actually, I should have the reference also. That was a paper published at IEEE, I think, in 2018.
I think the computer is in that direction.
Yeah, I tried, but. Okay, good. Yeah. So you see the reference here. Oops. You see the reference here. Yeah. That was a paper published at IEEE in 2018. Okay. Yeah, and this is something, of course, we don't want to have. Yeah, we don't want to be systems so fragile. We want machine learning systems to be more robust and therefore more trustful. And this calls for uncertainty awareness. We would like to have machine learning systems which are aware of their own uncertainty, which are aware of what they know and especially what they don't know. Yeah? And this, for the time being, is not really the case. Here is another example. This is an example we produced ourselves. So it's not invented. It's again a real example, but not published. We trained deep neural networks on state-of-the-art deep neural networks on ImageNet. And then you see here two examples. I mean, most of the time the system is doing a very good job and predicting correctly, but sometimes it doesn't work. So here, for example, this picture on the left is classified as a typewriter keyboard, which is obviously wrong. Every human immediately notices. Here on the right, the image is classified as a stone wall, which is again obviously wrong. This is not so bad. I mean, this can happen, of course. Even humans make mistakes in classification, also on images. But what isn't so good here is that the system is not only wrong, it is even very confident in its prediction. So it's over 80% in the first case and almost 90% even in the second case. So it's not that the system says, oh, I'm really quite unsure. I can give you a prediction here, but I'm not very certain about it. So maybe you would like to have a look yourself. It's not like this. Yeah. So what is missing here, obviously, is some sort of uncertainty awareness of the system. So what do we mean by uncertainty awareness and being aware of its own uncertainty, and how could we represent how could we let the system represent this uncertainty? So one thing is, of course, and this is already, I mean, commonly done, of course, in the field, is to predict, to deliver as a prediction a probability distribution over the possible outcomes instead of just making a deterministic prediction. So in the case of medical diagnosis, for instance, we would prefer the system to give a probability of positive and a probability of negative instead of just saying positive or negative. Or like in this case here, where we have three possible outcomes. This is about the prediction of the outcome of a football match. Yeah, you can have a win, tie, and loss for the home team, let's say, three possible events. And here we have on the left a probabilistic prediction, which is represented here by a point in this three-simplex. Yeah, so this is a barycentric representation of probability distribution. Every point inside this triangle corresponds to exactly one probability distribution. And if you know a bit about football, especially about German football, you might be able to give a quite precise prediction in terms of a single probability distribution that, for example, Dortmund will win against Bayern Munich, or the match will end with a with a tie, or Bayern Munich will win, which is most of the time the most probable event. If you know a little bit less about football, or for example about football in Portugal, because you don't know Portugal football so well, and you have to predict Porto versus Sporting Lisboa, you might be more uncertain. And one way, for example, to represent this uncertainty might be to not just commit to a single probability distribution, instead to provide a set of possible probability distributions. You find plausible candidates. In the literature here, this is called a creedal set. This is called a creedal set, a set of probability distributions. What might be another way to represent this uncertainty about the, let's say, right probability distribution? What might be another way, instead of using a set of probability distributions, and perhaps even more obvious, and perhaps also even more common? Any idea? The students? Let us start with the master students. No raised hand, the PhD students. And then at the end, I will come to the professors. There is a PhD student. Yeah, but range, I mean, a set is range, right? I mean, it's basically giving you, if you project to the individual dimensions, it gives you an interval, basically. If the set is convex, it gives you an interval for every event. An interval of probabilities for every event. Yeah. Are there any Bayesians here in the room? So a Bayesian would immediately say a set is not a good idea. You should use a distribution. Yeah. So a distribution over probability distributions, a second order probability distributions, this would be a very natural choice for people trained in probability, and especially for Bayesian people. A set, in a sense, is a more crude representation, if you want. But a set is easier to draw. This is why I took a set here. Yeah, and one important point I would like to make here is that going for such an extended representation, a second order representation of uncertainty, you are also able to express a complete lack of knowledge. If you know nothing, like for example, you have to predict Havaí FC versus Fortaleza. This is Fortaleza. This is Brazil. You don't know even the teams. You can't say anything. So, yeah. And this is a way to represent a complete lack of knowledge, to represent ignorance, which is not really possible with standard probability. Probabilistic approach. Some people will disagree. Again, the Bayesians in the room may disagree. But the alternative would be to define a uniform probability distribution, which is debatable. But I will come to this later in my tutorial, probably tomorrow, when I speak a little bit more about this distinction between aleatoric and epistemic uncertainty. This is, yeah, exactly one more comment I wanted to make. This set is basically representing what I'm going to call epistemic uncertainty, a lack of knowledge about, let's say, the ground truth, in this case, the ground truth probability. And one important distinction between, or one important difference between aleatoric and epistemic uncertainty is that the epistemic part is reducible. So you can reduce your epistemic uncertainty by gathering more information. Yeah. So, for example, you look into Portuguese football a little bit more, and then perhaps you will be able to reduce your uncertainty. I will come to this again later in my tutorial. Yeah, just to set the stage a little bit, as you can imagine, depending on what type of machine learning you are tackling, different problems of uncertainty representations arise. Different formalisms might be suitable. I am going to focus here mostly on the setting I already mentioned, the setting of supervised machine learning and predictive uncertainty, because this is really very relevant in many practical applications. So here you see again the basic setting. I showed already with this picture before. At the core of supervised machine learning, we have this process of model induction, which takes as input a set of training data. And this training data comes in the form of these tuples instance label. Yeah, so we assume to have labeled data. It's not only data that we need. This is a big misconception of many people who don't know about machine learning data science so well. They often believe you just put your data into the system, the big data, and then the knowledge comes out, or directly the money comes out, or whatever. This is, of course, not the case. Instead, you need to put in more. You always need some sort of domain knowledge, background knowledge. You need a clever induction principle, a learning algorithm, putting this principle into practice, and so on. The result of this induction process is a model here called H-hat, which maps from what we call the instance space X to the outcome space Y, so to which you can feed in a new instance for which the system will then make a prediction. So assuming that our underlying data generating process is a probabilistic process, it's a random process, a stochastic process, which is a quite plausible assumption. There is a question, yeah? Oh.
I mean, when you calculate probability of each event, it's ultimately, like, I think, first calculating the center of the mass of your sets, then pick the probability from there. If that's the case, then I was wondering, what is the fundamental difference between starting with a set, taking the center of the mass, only work with one probability distribution, or work with the whole set? I just didn't get the fundamental difference between the two, because at the end of the day, one probability is important for us for each outcome. Was it correct that the probability can be calculated from center of the mass?
I'm not exactly sure that I got everything acoustically. You mentioned the center of mass.
Mass of that set of probability distribution. There's a distribution on distributions.
Yeah.
So you can take kind of like the mean center of the mass.
Yeah.
That will be one probability distribution.
Mm-hmm.
So is it correct that probability of each outcome A, B, and C can be calculated either from this point, which is a distribution, or from the whole set, and the result will be the same? If that's if the answer to this question is positive, then I don't get the fundamental difference between the two approaches.
I mean, first of all, I mean, one important distinction is, of course, that averaging, I will come back to this, by the way, also later when I speak about the Bayesian approach. Averaging, or taking a weighted average or whatever, replacing a distribution by the mean or expected value, by doing so, you basically remove all information about uncertainty, yeah? Because you can have a wider distribution, a more flat probability distribution, or a more peaked probability distribution, both having the same expected value. But just looking at the expected value, you don't see how peaked the distributions are. And obviously, the more peaked the distribution, the more certain you are, the less uncertain you are. A second important point is that a set is not a distribution. This is what I tried also to make clear. A set is not a distribution, it's just a set, and the semantics is actually, I don't know which is the right distribution, but I know or claim it's any of the distributions inside the set. And an operation like averaging, for example, is not allowed for a set. It doesn't really make sense for a set. If you average the distributions inside the set, you are implicitly assuming a uniform probability distribution, which is an operation that is, strictly speaking, not allowed. So it's again a representation of uncertainty. So for example, the middle point here, the distribution 1/3, 1/3, 1/3, is the mean of, or the center of gravity of that distribution. But it makes, of course, a big difference whether I say, I am totally certain that the probability is 1/3, 1/3, 1/3 for the three events, or whether I say, I don't know anything. I can't tell you what is the correct or ground truth probability distribution. Makes a big difference, right? Okay.
I have a short follow-up question then. Can you explain, please, where it makes a difference? Kind of intuitively and philosophically, yes, there is a clear difference, but can you maybe bring an example of where that difference matters?
Yeah, I mean, it makes a big difference, for example, when, take this example of abstention. I mentioned this as one of the applications of uncertainty representation. You have a system which is allowed to abstain in case it is too uncertain. Yeah, and then it makes a big difference, for example, whether you say the probability that this patient has a certain disease is 1/2, it's 50%, because if you are certain that the probability is 50%, you might also be certain about the recommendation. Yeah, the probability, for example, is sufficiently high to start a treatment. Yeah, but this is, of course, different from saying I have no clue at all. I can't tell you anything about this patient. Yeah, if this is the case, then the system should maybe abstain from making any recommendation and hand over to the human expert, or, for example, to collect more information about the patient, make additional X-ray images, make more tests in the laboratory or whatever, but not taking an action, Yeah. So this is, of course, at the core of uncertainty representation. This is why we would like to have this uncertainty awareness. We would like not only to have a prediction, it's 1/2, but we would like to know how certain the system is about that prediction.
Excuse me, what's the rule of a model here? If you have a data with uncertainty, and if you want to have a prediction, for example, as you showed in the previous slide, we use a model, for example, mathematical model. Assume that we have a perfect mathematical model, this is assumption. But in the other hand, we have a data with uncertainty or large distribution.
Can you speak a bit louder?
Yeah, what's the rules of mathematical model here if we assume we have a perfect mathematical model? So how we can compare? So because right now, assume we have a model, so definitely with the perfect model, we have a perfect result. But in the other hand, we have a data to fit to this mathematical model, but the data has lots of uncertainty. So what's how we can manage this one with this sort of the data for the perfect model? Because the other problem here is the model itself, not the data.
Yeah. So when you say model, you mean a physical model or a model?
Any type of model for prediction.
Yeah. But my assumption here is, of course, but hopefully this will become more clear later on, that a prediction of this kind here, is coming from a model, from a machine learning model. The model, for example, could be, if you take again this example we had, a model, for example, could be a neural network. This is what you mean by a model, right? Okay, could be a neural network. This neural network here is making a deterministic prediction. It's just saying positive or negative. A better neural network probably would be a neural network which puts out a probability of positive and a probability of negative. And the point I wanted to make is that even if the neural network predicts these two probabilities, we do not yet know how certain the neural network is, or the learner is, about this prediction, whether this is a good prediction, a precise prediction or not. So at the next level, we could ask the system to predict a distribution of probability distributions, or, for example, a set of probability distributions, to have a clue about how certain or uncertain it is. And this has been done in the literature recently. For example, there are these Bayesian neural networks, they are called, which do not only predict a single probability, but which predict distribution over probabilities. Yeah? Wasn't that the question?
No, sorry, because when you want to predict something, so you said that we can use the neural network model, okay. But
Can you speak a bit louder? I can't hear.
In order to predict something, so we need model anyway. So, and here, assume we have a neural network model. Neural network model can be not perfect, true?
Yeah, yeah.
So, but assumption, we have a perfect model. For example, mathematical model that represent the dynamic of the system in order to prediction. In this case, what we can do with the data, for example, we have a model and we want to fit some parameters of this model with the data in order to find a good model in order to predict in the future, predict the future. So we have a perfect model. Usually, most we can rely on the mathematical model if we have a right mathematical model. But in the other hand, we have some data with uncertainty. So what we can do in this case?
On the other hand, what?
We have a data. We have a data with the. We have a model, and we want to fit this model with the data. Why we need to fit some data in this model in order to have or find the best model, true, in order to predict the future. But we have some data with uncertainty.
We have data what?
With uncertainty, with distribution of the data is not exactly the data in order to use in our perfect model, in order to find our perfect model. My question is more focused on the finding the perfect model in order to predict the future.
Yeah, so I'm not entirely sure.
Network, because neural network model itself can be.
Yeah, so once again, when you say perfect model, you certainly don't mean a neural network, right? You mean, for example, a mathematical model. So, for example, an ODE, yeah?
Yeah.
Yeah. So if you have such a model, then the story is, of course, completely different. I'm speaking here about, let's say, the standard machine learning setting. This is connected to this domain knowledge that I was mentioning. I mean, if you learn, then it's not only the data that is important, but it's also the domain knowledge or the background knowledge. This is what comes in here. So you know more about your domain. Yeah, for example, you have a mathematical model, then you wouldn't go for just training deep neural network, for instance. You would specify your model, and if you are certain enough, by the way, a perfect model, not sure whether this exists. You know this famous quote, all models are wrong, but some are useful, yeah? By the famous statistician Cox. Anyway, if you have a model in which you have a lot of trust and which you call perfect, then there would be no need to go for any data, right? You have your model, you believe it's perfect, you take it for making predictions. What often happens in practice is that you know your model up to certain parameters. You don't know exactly the values of the parameters of the model, yeah? Coefficients of an ODE or whatever. And then you go for data. Yeah? This is called sometimes data assimilation in some research fields. And you try to estimate the parameters from data. But then again, uncertainty comes into play because these estimates are only estimates. Yeah? And you would like perhaps not just to come up with a point prediction of a certain parameter, but perhaps with a distribution or a confidence interval of the parameter. And this uncertainty about the parameter will then translate into uncertainty about predictions. And this is exactly what I'm speaking about. So I would still claim everything that I said so far not only holds for the, let's say, standard setting of machine learning, but also for situations of that kind where you do have more background knowledge and not just go for a black box neural network, but you do what is sometimes called today physics-informed machine learning. Yeah? So I would say it still holds. Let me move on, perhaps things will clarify, and if you disagree, we can continue discussing in the break, perhaps. So a little bit more formally, and also to introduce some notation I'm going to use later on. The training data we are going to denote by capital D, by this calligraphic D. As I said, it consists of these tuples, instance and label, xi, yi. X is the instance space and y the space of possible outcomes. What the learner also needs is what is called a hypothesis space, and this is a subset of the set of all functions mapping from x to y in the case of a deterministic predictor, functions from x to the set of probability distributions over y in the case of a probabilistic predictor. This is the set of functional relationships the learner can choose from. The learner also needs a loss function which penalizes incorrect predictions. A loss function takes a prediction and a ground truth observation and compares the two and then penalizes the learner for any deviation. We call the loss function L, and given such a loss function, the goal, typically the goal of the learner, is to find an optimal predictor, a hypothesis H star, which has a low risk, or the lowest risk possible, where the risk of a hypothesis is defined in terms of the expected loss of its predictions, the expectation taken with respect to an underlying joint probability distribution over the instance space and outcomes, which we assume to exist, but which of course the learner doesn't know. Otherwise there wouldn't be any learning problem, then it would only be an optimization problem. The learner doesn't know, but we assume this P, capital P, exists, and this capital P is generating our data. Important special cases include classification and regression. In the case of regression, the outcomes are real valued, and the typical loss function used then is the squared error loss. Yeah, you penalize the learner by taking the square of the difference between prediction and observed outcome. Another important special case is classification, in which the outcome is categorical. And without loss of generality, we will denote the classes by 1 to capital K, 1 to 3 to capital K. If we have a K-class problem, a loss function, or the simplest type of loss you can think of in that case, is the 0-1 loss, which just checks whether the prediction was right or wrong, and then assigns a penalty of 0 or 1. This 0-1 loss is not easy to learn with because it's not easy to optimize. It's a function which is neither convex nor differentiable everywhere. So this is why to minimize in expectation this loss, what is often done is to use smooth upper approximation instead of the 0-1 loss itself, yeah, like the log loss, or maybe you heard about the hinge loss, which is used for support vector machines and so on. Question?
For classification, for example, can you have some sort of uncertainty in a way that, for example, if you're predicting what's in the picture, let's say you want to know if it's a cat or a dog, but it predicts it's an animal, or at least it's not a cup of tea, for example. It's in the ballpark of it. It predicts it's a cat. There's a dog in the picture. It predicts it's a cat, so it's halfway there. It knows it's an animal. It's not a cup of tea or a pile of logs. Can this be also kind of does this fit in the kind of theory of uncertainty?
Absolutely, absolutely. And if you remember in the very beginning, I did not only mention abstention as one application, let's say, of uncertainty representation, but also set-valued prediction. And this is exactly what you say. It's a set-valued prediction. You do not predict a single outcome like cat or dog, but you predict a subset. Yeah? And animal is just a name for a subset of things. This is especially convenient when you have a kind of hierarchy, a kind of taxonomy, which is the case in hierarchical classification, for example. You can imagine a taxonomy where you have, I don't know, humans, animals, and then animals, it's mammals and non-mammals, and so on and so on. And then instead of predicting a leaf node of that hierarchy, which would be a point prediction, you predict maybe an inner node, which corresponds to a complete subtree, and therefore for a subset of the leaf nodes. Yeah, exactly. This is another important application of uncertainty representation. And it does exist, yeah. Yeah, as I said already, often we do not just want to have deterministic predictions. We would perhaps prefer to have a learner which predicts probability distributions. And in this case, we have what we call a probabilistic predictor. In this case, the prediction of the learner for a given instance X as a query is a probability distribution over the possible outcomes. And in the case of categorical outcomes, in the case of classification, that would be a probability vector consisting of capital K entries. One probability, one estimated probability. Typically, if we put a head here, yeah, a common practice in statistics, if we put a head here, this denotes estimation. It's not a ground truth value, it's just an estimation. Then what is then in that case the task of the loss? The loss function then needs to compare not just two outcomes, but predicted probability with an outcome. So how well was the observed outcome predicted by the probability distribution? One example of such a loss is the logistic loss, the log loss, which is defined in terms of minus the log of the probability assigned to the class, the category that you actually observe. So if you assign full probability to the class you observe, the penalty is 0, and otherwise the penalty is positive. The lower the probability you assign, the bigger the penalty. So as I said already, the learner, of course, doesn't know the underlying data generating process, and this is why it can't just compute the optimal predictor, which we call the base predictor, the predictor with the lowest risk. Instead, it has to find other ways to come up with a good approximation, a good guess of this optimal predictor. And the point of departure here for most learning methods is what we call the empirical risk. It's the risk of a hypothesis on the training data. Risk meaning the average loss. This is what you can compute. Yeah? For any hypothesis A in your hypothesis space, the learner can compute how well does it perform on my training data? What is the average loss on the training data? And this is called the empirical risk. So just picking the hypothesis which has the lowest empirical risk typically doesn't work very well, because it comes with this well-known danger of overfitting your data to find a hypothesis which performs well on your training data, but which doesn't generalize well. And this is why, and this typically happens if you fit an overly complex model with too many degrees of freedom and so on. And this is why what is often done in practice is not pure empirical risk minimization, but regularized empirical risk minimization, where you find a hypothesis H hat, which minimizes this augmented loss, which consists of the empirical risk plus some penalty for complexity. So you try to find a good trade-off between the complexity of the model and the performance on the training data. Yeah.
I just thought that maybe for some of the audience it would be good to relate this also to the training of a deep neural network in particular. So the hypothesis there is a particular set of weight values for the neural network, right? So the loss function is log loss, as you said, which is also known as cross entropy. And then that's exactly how neural networks are trained. You just have this training loss, which is the average loss over all the training examples, which you call empirical risk. And then you also have these regularizers, which are plenty in the neural network space.
Yeah. I deliberately did not take neural networks as an example because they are somehow no, it's fine anyway. But the problem a little bit with neural networks is, in my opinion, they call for a deeper explanation because they are in contrast with classical theory. So they should hopelessly overfit your data because they have so many degrees of freedom. Surprisingly, they don't. Still, often you need some regularization, sure. So this makes neural networks, in my opinion, a specific case, but nevertheless, yes, you can instantiate the whole setting, of course, with neural networks. In this case, the hypothesis space consists of all neural networks that you can obtain as instantiations of your topology by putting weights on the edges of the neural network. Your hypothesis space eventually is a parameter space. The loss that is typically tried to minimize with neural networks is indeed the log loss I just mentioned on my previous slide. And yes, it's not just the empirical risk that is typically tried to minimize, but a kind of regularized risk. Because, as I said, these neural networks, of course, have a tendency to overfit the data because they are so flexible. Many neural networks have way more parameters than data they trained from, where every statistician would say, oh, wait, this can't work. Yeah. Yes, regularization is certainly needed. There is another question?
About the definition of empirical risk, before you had a continuous definition where you had the integral over the loss function for all the probabilities, but here you have like a sum of these loss functions and you don't have the probability itself in this discrete version.
Yeah. We have a sum instead of an integral because the training data is always assumed to be finite instead of infinite. The instance space is, of course, typically an infinite space. And we don't have weights here because it's the weights, so to say, or the probabilities are implicit in the frequency of the data. So you can assume that if a certain tuple xy has a higher probability than others, it will occur more often in your training data, or if a certain region within your instance space has a higher probability, there will be more examples in your training data from that region than perhaps from other regions. So probability is somehow implicit in this sum in terms of the frequencies of examples from different parts of your instance space.
Okay.
Yeah? Okay. Yeah, but thank you. Yeah, good question. So regardless of the principle, let's say whether you do regularized empirical risk minimization or whatever induction principle your learner applies, it will come up with a guess for, let's say, the best hypothesis, which we call H-hat. Hat because it's a guess, is what the learner guesses. So it takes, for example, a specific neural network, yeah, with specific weights. This guess, of course, will normally not coincide with a true risk minimizer, which we call H star. This is the truly best predictor, the truly best model you can have, the model within your class of models which makes which has the lowest risk, yeah, which performs best predictions on average in terms of the underlying loss function you specified. So these two will typically not coincide. And therefore, if your neural network gives you such an H-hat, there remains uncertainty regarding, of course, how good that is. How close is your H-hat to the H star, the best you could have? And correspondingly, what is actually the risk? How close is the risk of H star to the risk of the truly best model H hat? And this uncertainty about the model then translates also into uncertainty about the prediction. If your H hat gives you a prediction Y for a new query instance, which is called here XQ, then you may wonder how good is that prediction compared, for example, to a prediction that comes from my truly best model H star. This is what I called predictive uncertainty earlier. Yeah? And now we would like, let us have a closer look at what, let's say, different types of uncertainty we can have and what actually contributes to the overall uncertainty about models and about predictions. Before that, let me make another remark, namely that a precise specification of your problem setting, including also the underlying assumptions you make, is always a very important prerequisite for proper uncertainty representation and quantification. So what do I mean by that? I introduced this setting of supervised machine learning very briefly. One implicit assumption, for example, in this setting is that your data is IID. So it satisfies the assumption that these tuples xi, yi are independent and identically distributed. This is a very important assumption if you want, for example, to use your model for making future predictions. Without this IID assumption, for example, the future could be completely different from the past. And if that is the case, you can't assume your model to make accurate predictions of the future. And therefore, of course, you also can't assume your model to represent its uncertainty in a proper way. Here is another example. So if you look at this picture here, what it's illustrating is that you have seen some positive examples, the red crosses, and you have seen some negative examples here, the black circles. And now imagine you have to make a prediction for this data point here. So what would you predict? If you look at the picture, you probably will say, okay, this seems to be a somewhat atypical example. It's not very representative neither of the red nor the black class, but it's of course much closer to the red class. So if you have to decide between red and black, you will probably say, I'm quite confident that this is a red example, a positive example, right? So, and you are relatively certain about this. It's very uncertain that this is a black example. However, you implicitly make the assumption here that there is only black and red, and there is no possibility for any additional class that you maybe haven't seen at all in your training data so far. So if you weaken this assumption and you say, I am in a setting of what is nowadays sometimes called OOD, out of distribution data or novelty detection or whatever you want. In any case, you allow, you consider this possibility that you will observe in the future examples of new classes that you have never seen before, which is, by the way, a realistic assumption in many applications. Then the situation will completely change, and suddenly you will say, I am no longer that sure that this is a red point, a positive example. It might be a positive example, it might be red, but perhaps it's also a third class I haven't seen before. So it might be a completely different color. And then your uncertainty increases under this assumption. Yeah, and this is just meant to show that you cannot expect to have a sound, let's say, representation and quantification of uncertainty without making your assumptions precise. Changing assumptions will not only mean changing predictions, but also changing uncertainty representation. This IID case I already mentioned. So now coming to these different sources of uncertainty. Even if you know everything, our assumption is typically that there is no deterministic dependency between instances and outcomes. So even if you know how they relate to each other in terms of this probability distribution P, the dependency is stochastic. So the conditional probability of a certain outcome Y, given a query X as an input, is a probability. Yeah. This is because we typically assume that the instance information, for example, the features describing an object, do not suffice to determine the class, in the case of classification, for instance, in a unique way. So, for example, if you classify, I don't know, people according to their gender, whether it's a man or a woman, and the only features you have is the height and the weight, then you can't always be certain, of course, yeah? Giving a certain height and weight, it might be a man or a woman with the corresponding probabilities, but you can never be 100% sure. This is why, even if you know everything, even if you know the ground truth probability distribution, which generates your data, uncertainty in the outcome will remain. You can't predict deterministically. Yeah. So the best prediction then you can make is produced by what we call the Bayes predictor, or more specifically the pointwise Bayes predictor. What is this Bayes predictor doing? We call it F star here. The Bayes prediction, the pointwise Bayes prediction for a query instance X is given by the outcome Y hat, which minimizes the expected loss. So this is the best the learner can do. Yeah? And the expected loss is given by this integral here over, let's say, over the outcome space, which is just a sum or a weighted sum in the categorical case. It just picks that prediction, that outcome for which the expected loss is minimal. This is called the pointwise Bayes prediction. So here is a simple example. Imagine our instance space is just a real number line, so we observe instances just in terms of, or characterized in terms of a single feature. For example, the height. I don't know, the height of people. Yeah. And we have two classes. I don't know, Germans and Estonians. I don't know who is taller on average, but anyway.
Estonians are taller.
I guess so. Yeah. At least they are stronger. Yeah, but probably also taller. Or the Dutch people. I think the Dutch are the tallest in Europe. I don't know. Anyway, you have two groups of people. Since we only have two groups, we are in the binary case. So we have two class labels. Let's call them -1 + 1. Let us assume also that the priors are equal. So 50% prior probability of the two classes. So the two populations are equally big, let's say. In this example, the one class has a normal distribution with mean 180, the positive, and standard deviation 10. And the other class with mean 160 centimeters and standard deviation 10 also. The hypothesis space is consisting of simple threshold classifiers. So the learner can choose just one parameter, the threshold, and then say everything above the threshold I classify as positive, everything below the threshold I classify as negative. So if you know the distributions, you know everything, you know the data generating process, the learner typically doesn't, but if you know, then what is the Bayes predictor? What does the Bayes predictor look like? The pointwise Bayes predictor look like? What does it look like? You can already see from the image. And what I indicated below the image, it's quite obvious that the optimal threshold here is in the middle. It's 170 centimeters. So on the right, the prediction will be positive or red. On the left, it will be negative. Why? Because the conditional probability of positive, given a certain value x, is bigger than the conditional probability of negative for values exceeding 170 and lower, below 170. By the way, what will happen if we don't use a simple 0-1 loss, but we predict a false positive stronger than a false negative? What will happen to the threshold then? Will it remain the same, or will it move to the left or to the right? So this is often useful in practice. So in medical diagnosis, for example, you may say that a false negative, you say the patient is healthy, although it isn't, is worse than a false positive. You could say, for example, yeah. If that is the case, then you will have a tendency to make more positive predictions. You will tend to predict positive, even if the conditional probabilities may be a little bit lower. So the threshold will move. Yeah, the threshold won't remain in the middle, but it will move. Okay, but in our case, let's take simple 0-1 loss. And in this case, yeah, if we take simple 0-1 loss, the pointwise Bayes predictor will be given by the threshold classifier with threshold 170 centimeters. And this coincides with the Bayes predictor. So the best predictor we can find in our hypothesis space. Or in other words, the pointwise Bayes predictor is an element of our hypothesis space. But this is not always the case. As, the Bayes predictor, the best hypothesis, the best model in our space, does not necessarily need to coincide with a pointwise Bayes predictor. And this discrepancy between the two, the H star and the F star, this is connected to what we call model uncertainty. It's connected to the question, what is actually the right type of model to work with? How should I specify my hypothesis space? Yeah, and yeah, we call this uncertainty model uncertainty. And because there is model uncertainty in practical applications, we cannot always guarantee that the H star and the F star coincides. And if we train probabilistic models correspondingly, we cannot always guarantee that the true conditional probability of a certain outcome given a query instance X coincides with the probability we predict, yeah, with a probability that is predicted by our Bayes predictor, by the best predictor within our hypothesis space. So here is again our example. Now suppose that we change a little bit the two distributions. Now the one distribution is normal with parameters 180 and 15, so it has a slightly bigger standard deviation. The other distribution is 170 and standard deviation of 8. The two distributions look like this. Yeah. And now what is the pointwise Bayes predictor? It's again indicated here below. You see that the conditional probability of the positive distribution is bigger to the right, but also to the left, yeah, because it has a lower standard deviation. For very small values, it again exceeds the probability of the negative class. And therefore, the optimal pointwise Bayes predictor cannot be realized by our learner, which only can choose a threshold classifier and say left is negative, right is positive. What would we need? We would need a richer hypothesis space, for example, a hypothesis space consisting of interval classifiers. So we would need a classifier which has two parameters instead of only one, yeah? A left boundary of an interval and a right boundary of an interval. But if we work with a simple threshold classifier, we can't realize the pointwise Bayes predictor. The Bayes predictor, the best predictor within this space of threshold classifiers, is still the one which makes a cut here, as before. Yeah? And it will predict incorrectly here on the left-hand side. So, yeah, as shown by this example, the Bayes predictor, the best the model can actually produce, doesn't always coincide with the best possible, the pointwise Bayes predictor. And another source of uncertainty is, of course, that the learner doesn't know the best it can do. It doesn't know the H star. It doesn't know the H star because it doesn't know the underlying data generating process. It only sees the data. And from the data, it makes a guess. The guess, you remember, we called H hat. And again, there is a discrepancy between H hat and H star. Like here, for example, where you fit a simple linear model to a binary case again. If you have seen only little data, the best, presumably best separating hyperplane may deviate from the actually best, which you could get closer to once you have seen more data. Yeah. And this uncertainty, this discrepancy between the H star and the H hat, this is what we call approximation uncertainty. So here is again our example. Now suppose the learner doesn't know these distributions, doesn't know that, it perhaps even doesn't know that the two distributions are Gaussian. The learner only sees data, so it only sees these training data points here, these realizations from the two distributions. This is what the learner sees. And a learning strategy, for example, could be to find the intermediate point between two observations for which the empirical loss is minimal. So it makes the minimal number of mistakes on the training data. This could be a reasonable learning strategy, right? And in this example, this would be this H hat here. Yeah, it makes, you see, it makes one mistake, namely here, and all the others are correct, so it only makes a single mistake. The empirical error is 1, or 1 over the number of examples, whereas the truly best H star is here, and there is a discrepancy between the two. Okay, so to summarize this discussion, there are various sources of uncertainty which contribute to the overall uncertainty in the model produced by our learner and in the predictions that are produced by that model. Here you see as an illustration, this is our hypothesis space, the region here shaded in gray. It's a subset of the space of all functions, mapping from x to y or from x to the probability distributions over y. The H star is the best the learner could find within that space. So for example, the best neural network with the best parameterization. It's not necessarily equal to the best one could achieve in principle. Yeah? It may deviate from the F star, the pointwise based prediction. And in addition, what the learner will produce is not the H star, but the H hat, which is derived from the data. Yeah? And there is, in addition, therefore, approximation uncertainty. Okay. Once again, an illustration summarizing what I just said. So here in the two-class scenario, the F star might be this nonlinear green function here. But if the learner can only fit a linear model because you restrict your hypothesis space to linear functions, linear separating hyperplanes, the best it could achieve, for example, is the blue one here, the H star. And it's not even that what the learner, of course, will deliver, but given the training data, it will perhaps deliver here the H hat. Yeah? And the H hat obviously differs from H star and also from F star. We could even distinguish these different sources in a more fine granular way if we want. So for example, I won't do, but I just want to mention that you could not only distinguish this, what I called model uncertainty and approximation uncertainty, but if you want even a bit more fine granular. So for example, what contributes to this approximation uncertainty is not only the data, the amount of data, the quality of data, etc., but also the algorithm. So there is also something you may want to call algorithmic uncertainty. What do I mean by this? Is that typically this learning of the H hat comes down to solving some sort of optimization problem. Training a neural network, for example, for a given data set is a kind of optimization problem. And you cannot be sure, of course, depending on what algorithm you apply, that you will really come up with the optimum of that optimization problem. Perhaps because your function, your loss function or regularized loss function you want to optimize is a non-convex function, has local optima and so on. So then you can't be sure that you even find the optimum. And again, this is a source that contributes to the uncertainty about the quality of the model learned in the end and the predictions that are derived from that model. Okay, so this concludes the first part of my presentation. It took me more time than I thought, so I will, as I said, probably skip a little, or let's see. I mean, I will make, after this first part of the tutorial, I will replan the rest of the tutorial. For now, I see I still have a couple of minutes left, so I will continue. Yeah, no? Yeah.
Half an hour you have left.
Yeah, yeah. Yeah, but I would like to ask you whether there are any more questions still here. I hope you have a basic understanding. Yeah, there is.
Yeah, thanks. I was wondering about this example of labeling the images. I guess these algorithms also, they take the input image and then they transform it into something simpler for them, like 100 by 100 pixel grid. What type of uncertainty is that? Because it kind of blurs the image a bit. If I take my glasses off, I would also say that it's a stone wall, not the pile of logs.
Yeah, okay. I mean, this is, you mean, of course, yeah, what you mean is that the raw data, the image, for example, is typically pre-processed into a representation that is then fed as input to the learning algorithm. Yes. Yeah, so this uncertainty is uncertainty that relates to the data, I would say. It's part of the data and the data representation. And it's an interesting remark. I think I will also come to this issue a little bit more towards the end of the tutorial, again, when I speak about epistemic uncertainty and aleatoric uncertainty. If, for example, you condense your representation a lot, so for example, you go from this very high dimensional space of raw data to a very low dimensional space, you may lose a lot of information. And this will contribute to uncertainty in the sense that, for example, the two classes you want to distinguish, let's say you want to distinguish cats and dogs, will highly overlap in this low dimensional space. And this will lead to a high degree of what I'm going to call aleatoric uncertainty. If you remain in a higher dimensional space, the classes might be better separable there, but finding the best representation then may become harder. So this may lead to an increase of epistemic uncertainty. Yeah, so the representation is very important from this point of view. As we all know, you need a good feature representation in order to learn an accurate predictive model. Again, neural networks are a little bit specific in this regard because typically they are applied more or less directly to the raw data and find good intermediate representations themselves. So they play, again, a specific role. But yes, data representation certainly contributes not only to the uncertainty in the end, but also to these different types of uncertainty.
I have a question about what is your take on these model complexity and penalization of more complex models, and how does that relate to this uncertainty? Are there some ways how you should favor what kind of complexity penalization, and does it relate somehow?
I mean, here, if you look again at this, no, so wrong direction. If you look again at this summarizing picture here, what does it mean to regularize? Not exactly one-to-one, but roughly speaking, it means to restrict your hypothesis space. So if you make this space, the gray region here, if you make it smaller, then this can have a positive effect and a negative effect. It has a negative effect if your truly best predictor, the F star, has been in your hypothesis space and now suddenly it's out because you restrict too much. This means you regularize too much, roughly speaking. And then it has probably a negative effect for the learning process because the learner hasn't a chance anymore to find this truly best predictor. If the F star remains inside your hypothesis space, although you narrow it down, it will have a positive influence. Why? Because the learner now has an easier job. It searches in a smaller space of candidate hypotheses. And this typically is then easier for the learner. Roughly speaking, you can, what all learning methods eventually do is searching the space of candidate hypotheses. And the bigger that space, the harder the problem, and the higher is the chance that the H star, the model that is found by the learner, will deviate from the H star. So if you regularize more, you tend to increase the model uncertainty but decrease the approximation uncertainty, and the other way around. And this is why finding the optimal compromise, the optimal regularization, is the important thing to do. And the question how to do that isn't easy to answer. But yes, you are certainly right. This is a very important point, not only with regard to accurate prediction, but also uncertainty representation. But I can't tell you how to do that in an optimal way. I mean, this depends also on the type of learning method, of course, you apply. There are more theoretical approaches to optimal parameterization, regularization, and so on from statistics, different sorts of information criteria. But in machine learning, typically people go more the empirical way. You do validation, cross-validation, you optimize hyperparameters, and so on. Okay, are there any more questions? Otherwise, I proceed. So here is an overview of the rest of the tutorial as I originally planned it. As I said, up to some replanning, depending on how it goes and how quickly we proceed. I would like to first tell you a little bit more about how to learn these probabilistic predictors. As we said, and we all agreed, it's better to have a probabilistic predictor than a deterministic predictor. But the question is, how do you train them? How do you learn them from data? What are common ways to do that? Then the third part, I will touch on only briefly the topic of calibration, which is something that Melis is the world expert on and will give you a presentation on Wednesday, I think. And this is why I will be very short here. You can see, you can consider his presentation on Wednesday maybe as a completion of my presentation today, which is the idea of improving the probabilities predicted by a machine learning model in a kind of post-processing step. So making them better, calibrating them. Then I will speak about conformal prediction. Who of you ever heard about conformal prediction? Very few people. That's good for me, because then I may have to tell you something new. This is really a very interesting methodology, I would say, which is actually not so new. It's around till, I don't know, more than 20 years or so. But surprisingly, it's only quite recent that machine learning people have jumped on it. And now it's booming a lot. It's now, you find last 2-3 years, you find regularly papers also at the major machine learning conferences on conformal predictions, conformal prediction tutorials are organized and so on. And the last part then will be devoted to this distinction that I mentioned already a couple of times, aleatoric uncertainty versus epistemic uncertainty, and the question how a learner could represent its own uncertainty about, let's say, the right probabilistic prediction, its own epistemic uncertainty. All right, so this is roughly the plan, and now I will use the last 15-20 minutes or so to start this second part, which of course I won't completely go through, but at least let us make a start. So once again, to remind you what we mean by probabilistic models, probabilistic predictors, is models H hat, which take an instance as an input and then produce a probability distribution over the possible outcomes as an output. So if we have a 4-class problem, for example, 4 possible outcomes, and we train a neural network, it will deliver us 4 values for probability degrees, 1 for every class. And this is a point, if you want, this is a single model, a point within our hypothesis space. Yep. So therefore, since it's a single model, a single probabilistic prediction, this model will capture what we call aleatoric uncertainty, but not yet epistemic uncertainty. It picks a single model, but it doesn't tell you how certain or uncertain it is about this choice of the model. So in a sense, if you want, the learner will pretend that it's completely certain about the choice of that particular model, of that particular neural network, for example. So it claims to have basically no epistemic uncertainty. So how could we produce these probabilistic predictors? There are, of course, many ways, and probably many of you have already encountered such methods in the literature or in courses. One way is to, let's say, extend in one way or the other simple standard machine learning methods, like, for example, decision trees. You all probably know decision trees. You fit a tree or fitting a tree to training data here in 2 dimensions. You have data characterized by 2 real valued features, let's say x1, x2, coming from 2 classes. Fitting a tree means recursively partitioning your data by making splits of regions of this instance space here. So first, for example, you may distinguish whether the x1 value is exceeding 9 or not, and then you have this split here. You have the data to the right, the data to the left. The data to the right, you again recursively split into 2 parts, making here this split corresponding to the value of x2, and so on. And then you come up with a partition in the end, and with a tree that may look like this. And to obtain a deterministic prediction, you will typically go, if you have a new instance to classify, you will look at the leaf node it ends up in, and then you will predict the majority class, the class that you have observed more often, most frequently. If you want to have a probabilistic prediction, what is the obvious thing to do? You do not just look at the majority, but you look at the relative frequency. So if, for example, your new query instance goes into that leaf node here, and you have seen 7 positive examples in that region and 8 in total, you would be inclined perhaps to predict the probability for positive of 7/8. So, and in this way, you will be able to predict probabilities. At least, let's say, pseudo probabilities, because you can imagine that these probabilities will normally not be very well calibrated. Yeah? So why, for example, do you have a clue, an idea for why these probabilities that you estimate in this way will probably be biased, and in which direction? The probabilities that you estimate in this way are will probably be biased, but why? Yes, of course, the less data you have, the less accurate these probabilities will probably be, which means they are probably not accurate, but it doesn't immediately mean they are biased. What I mean by bias is that they are systematically biased toward a certain direction. And they could be biased, for example, toward the middle. There could be a tendency of the learner to produce predictions around 1/2. I don't know for what reason ever. This will probably not be the case, but what will probably be the case here, if you... Yeah, this will contribute, of course, to the reliability again. Yeah, so the less data you have, and this is a fragmentation problem, also you have with decision trees, the more you fragment, yeah, the less data you end up with in a leaf node, and then the prediction will become very unreliable. If you do not fragment so much, then you have the problem that then you have the advantage that you have more data. For example, you could have you could have taken the whole region here as a leaf node, then you have much more data in. You can estimate probabilities from, but then of course the probability estimates won't be very accurate because it's obvious that you don't have the same conditional probability of positive everywhere in that region. Yeah, so fragmentation problem. But again, my question regarding the bias, why? Yeah. Yeah. Yeah, you're right. Of course, it depends on the algorithm. I just said, I mean, this is what most decision tree learners do, this recursive partitioning. I didn't specify that more. But what they all are doing, basically, is trying to find splits which make the regions as pure as possible, where pure means that you have one really prevalent class and the other one doesn't occur very often, preferably even not at all. And because all these learning algorithms are exactly following that strategy, the estimated probabilities will probably be biased toward the extremes. Yeah? So biased toward either 0 or 1 for positive and negative. So by predicting these probabilities, the learner will somehow pretend to be more certain than it actually should be, because it deliberately partitions in such a way that these estimated probabilities become extreme. There are ways to prevent this a little bit. So for example, instead of just delivering the relative frequencies here, what is often delivered as a prediction is a Laplace correction, so-called Laplace correction of these probabilities and so on. Yeah, so and in this way, in this ad hoc way, you can generalize, let's say, most existing machine learning methods to extract probabilities from these models instead of just deterministic predictions. But how can you how can you learn probabilistic predictors in a more principled way? One approach, quite common in statistics and also in machine learning, is maximum likelihood estimation, which you probably all know very well about. So imagine that we can parameterize our hypothesis space so that we can identify, uniquely identify every hypothesis with a certain set or vector of parameters theta, like in the case of a neural network, yeah, where the parameters are the weights on the edges. In the case of a big neural network, it's a very high dimensional parameter vector, but in any case, it's a parameter vector of a fixed dimension, which uniquely identifies your hypothesis, which we then denote by h theta. This is the model, the predictor that is parameterized by theta. So suppose that we can represent hypotheses in this way, then learning actually comes down to parameter estimations. We would like to find the best parameterization theta. How can you do that? A very principled approach to parameter estimation in statistics is maximum likelihood estimation. The maximum likelihood principle suggests to pick that parameter which has the highest likelihood. And the likelihood of L of theta, the likelihood of a parameter vector theta, is defined in terms of the conditional probability of the data given the parameter vector. So it's not a probability of the parameter vector, it's the probability of the data given the vector. This is why it's called likelihood. Maximizing the likelihood is, of course, nevertheless a reasonable principle, because the idea is basically to pick that parameter under which the data you really observed, you actually observed, becomes most plausible, most probable. So this is a reasonable principle. We call the ML, the maximum likelihood estimate, we call it theta hat. And this maximum likelihood estimation is not only intuitively plausible, it also has a number of appealing statistical properties, so it's asymptotically efficient and so on. So it has a number of desirable statistical properties. So what does it mean to find the maximum likelihood estimate? Finding the maximum likelihood estimate means solving an optimization problem. So we have the argmax here. So we need to maximize this probability. If we make the IID assumption, meaning that we assume that our training examples xi, yi are independent of each other and identically distributed, then the probability of the training data is the product of the probabilities of the individual examples. Yeah? So we need to maximize this big product. And maximizing a product is not so convenient, especially if you apply gradient-based methods, because you know from school that taking derivatives of products is not so nice. Taking derivatives of sums is way easier. This is why you normally don't maximize the likelihood, but the log likelihood. Taking the log of the likelihood doesn't, is a strictly monotonic transformation, so the maximizer remains the same. But the nice thing is that the log of the product is the sum of the logs of the probabilities, so you have a sum now. And taking the derivative of a sum is the sum of the derivatives, so optimization becomes much easier. One thing, one side remark I wanted to make already with regard to uncertainty representation is that you, from the maximum likelihood estimate, this is an important result from classical frequentist statistics, is that from the maximum likelihood estimate, you can also extract some information already about the certainty or uncertainty about the maximum likelihood estimate. So if you go with the maximum likelihood estimate, the theta hat, then the learner delivers a single probability, a single model, single probabilistic model, a neural network, for example, with certain weights. And the neural network, given a query instance as an input, will predict a probability distribution, a single probability distribution. And I said repeatedly that this is nice, but perhaps not enough, because we would also like to have some information about how certain or uncertain this probabilistic prediction actually is. You can extract some additional information in that direction, and this is called the Fisher information. Namely, it's known that the distribution of this maximum likelihood estimate, the theta hat, this is a statistical quantity which depends on the data, so it does have a distribution itself. Is known to be asymptotically normal, more specifically this expression here, the square root of n, the number of training example, times the difference between your estimate, theta hat, and the true parameter theta, converges to a normal distribution with mean 0 and covariance matrix, which is the inverse of this so-called Fisher information matrix, which is the negative Hessian of the log likelihood of the true, the log likelihood function at the position of the true parameter theta. So roughly speaking, it means that the more peaked the likelihood function is at your at the estimate, the more certain the learner is, and the less peaked, the more flat the likelihood is, the less uncertain. And this you can see from confidence regions you can extract or construct around your estimate using this Fisher information matrix. Yeah. If the learner is very certain, this region is very narrow. If the learner is less certain, the region is more broad. Yeah, okay. Yeah, just as a side remark. And if you want, you can also extract some quantitative measures, single numbers, telling you something about the certainty or uncertainty of the estimate. For example, the trace of this Fisher information matrix, or the of the inverse actually, or the smallest eigenvalue. Yeah, inform you about the uncertainty. Yeah.
Computationally, can you kind of say a few words about how hard it is in practice to compute all this?
Depends, of course, a lot on how your likelihood function looks like and how, let's say, how complicated the derivatives are. So here you see that here you have a log, the log of a probability. And taking the derivative of a log can already end up in a quite complicated expression depending on how this probability looks like. But it really strongly depends on how your parameters here enter this probability, yeah? In which way they enter the probability. But this can already be a complicated expression, and in many practical cases it is. And then, yes, I mean, your comment is, of course, has a good reason. Then going for the second derivatives, which you need for the Hessian, becomes even more involved. But often, I mean, it's a matter of if you have to derive these expressions by hand, yes, can become a little bit complicated. But computationally, I wouldn't say it's that much of an issue. The expressions can become complicated, but in many cases, you even have, you can derive them even analytically, and then yeah, sure, there is some computation involved, but I don't know, frankly speaking, how it is in the case of neural networks. And so when you have really such a huge amount of parameters, this is not what is typically looked at in classical statistics. The classical models for which you do maximum likelihood estimation in statistics don't have that huge number of parameters. And then it's, of course, more doable. Yeah. Okay, so I would next what I would like to do is to give you one example of maximum likelihood estimation, which is a very important example, namely logistic regression, which is a standard method, I would say, for classification in statistics, but meanwhile also in machine learning. I see that time is almost over, and this is why I would suggest to make the break here and then continue after lunch. It's not the best cut point I could make, but it's hard to find the ideal cut point, given that I can't fully control how time flows with the discussion and so on. Yeah.